These are the video notes for 7.2 graphing reciprocal functions. I know we're in the unit on rational functions. However, the reciprocal function is the most basic form of a rational function. So we're going to start off graphing those first. Let's look at the parent function. It's f of x equals 1 over x. So you can see that x and y are going to be reciprocals of each other. Let's graph some parent points. We'll pick the points 2, 1, 1 half, negative 1 half, negative 1, and negative 2. And at least let's look at what the x values do that are positive when we plug them into this equation. So if I plug in 2, I get 1 over 2, which is 1 half. If I plug in 1, I get 1 over 1, which is simply 1. And if I plug in 1 half, we get 1 over 1 half, which flips the bottom fraction and gives us the answer of 2. So, and then the same would occur with the negative values. You get the same answers, they just be simply negative. Now, if we plot those points, I'm going to get 2 and 1 half, 1, 1, and then 1 half and 2. In terms of the negative values, I'd plot 1 half and, negative 1 half and negative 2, negative 1 and negative 1, and negative 2 and negative 1 half, and connect the dots. And you'll see that I have two branches. They're the same shape, same size, they're symmetrical. One happens to be in quadrant 1, and the other one is in quadrant 3. Now, notice that this graph sort of resembles something that we've looked at before. It actually looks very much like the shape of a hyperbola that's been rotated, say, about 45 degrees. So hopefully you remember that from when we did conics back in the fall. Also, let's talk about the domain and range. So the graph has an arrow that continues onward to the left and another arrow that continues on to the right. So the domain is actually all real numbers except for where x equals 0. So right here, it never gets to this point right here. Notice I'm using set builder notation this time. It's a little bit easier to write those exceptions when you use set builder notation. And let's look at the range. The arrow points down and it continues to go downward, and the arrow points up and continues onward, upward. So, but the graph never reaches 0 again. So the range is the same, all real numbers, except for where y would equal 0. So that's the exception. That means we have a vertical asymptote at x equals 0, or the y-axis, and a horizontal asymptote where y equals 0, or the x-axis. Now, why is that the case? If I plugged 0 in for x here, we'd have 1 over 0, which would be undefined. So that's an area where the graph would be undefined, and it makes it an asymptote. By the same token, if we let f of x or y equals 0, there is no x value, or 1 over x, that will allow us to achieve a 0 over on this side of the house. So since we can't find an x value that'll make this true, that means that y equals 0 is also a situation that would be undefined and result in a horizontal asymptote. Now, let's move on and talk about the standard form of a reciprocal function, because most of the time we're transforming our graph. We're usually not working with the parent graph. So h is your horizontal shift, moving the graph from left to right. If down here we have, and then, so here's our equation, f of x equals a over x minus h plus k. If the value here, if it's x minus a number, then that's going to shift the graph to the left. If it's x plus a value, say x plus 3, it will shift the graph to the right. For k moves the graph up or down, so it's a vertical shift. So in the case of a positive value, it would move the graph up. If it's negative, it would shift the graph down. Now, let's talk about the a value, so the number on the top of the fraction bar. A is negative. That means that the function is going to be reflected across the x-axis. So remember, we talked about the branches being in quadrants 1 and 3. They'd end up in quadrants 2 and 4 instead. And if a is greater than 0, so it's a number greater than 0, like say 2, 3, 4, 5, that means it's going to be a vertical stretch. If the number happens to be between 0, 1, say 1 half, or maybe 0.75, then it represents a vertical compression or shrink. Now, how do we find the asymptotes? So here it was easy, right? It was just x equals 0 and y equals 0. Well, really, you can find the vertical asymptotes by looking at your h and k. So the vertical asymptote is simply going to be x equals h. So to find it, I'm going to take the equation x minus h, set it equal to 0, and solve for h. So that's where that value is going to come from. And then the horizontal asymptote is going to be y equals k. So we're simply going to take the k value as is, and we don't need to do any solving there. Okay, so let's look at some examples so this starts to make sense. So in these graphs going forward, we'll use the isotopes as a guide for our graphing, and we're only going to graph 2 points per branch. So I'm going to use the x values 2, 1, -1, and -2, and I'm going to leave out the 1/2 and -1/2. We included those just so you could get a better perspective of what the reciprocal function graph looks like. Okay, so let's get started. So I've got f of x equals 1 over x minus 2. So the transformation here is going down 2. So I'm going to take my x values, these are my parent points, 2, 1, -1, and -2, and I'm going to plug them into the parent function 1 over x, and then I'm going to subtract 2. So we've got the parent points up here, so we could actually just copy down 1/2, 1, -1, and -1/2. Those are our parent points for the y value. And then from each of those, simply subtract 2. So if we do that, we'd end up with -3.5 or -1.5, a -1 here, -3, and then last but not least, -5/2 or -2.5, depending on how you want to look at it. Now, let's talk about the domain. The domain is going to be all real numbers except where x equals 0, because we're not adding or subtracting any value for x. So the vertical asymptote will simply be x equals 0. However, the range is going to be a little different. So the range is going to be all real numbers except where y cannot equal a -2. So again, we're taking the k value as is. That means the horizontal asymptote is going to be where y equals -2. So first thing I always do is I'm going to graph my asymptotes first. So at x equals 0, or the y-axis, I'm going to do a dashed line. Hopefully you can see it. I'm also going to do another one where y equals -2. So find -2 on the y-axis and do a horizontal dashed line to go ahead and graph your horizontal asymptote. And then we're going to graph 2 points. So I'm going to graph the point 2 and -1.5, 1 and -1. So that'll be the 2 points for this branch. And then I'm going to come down here at -1, -3, and -2 and -2.5, and I'll get those 2 points. And again, connect the dots, and also making sure that you keep the branches inside the isotopes so they're not touching or intersecting or crossing the isotopes in any way. So that's important. All right, let's try another one of these. We have y equals 1 over x plus 3. So what are we doing here? So remember our chart up here. It's plus 3, so we're going to the left 3. So I'm going to subtract 3 to move the graph over to the left from each of my x values. Remember, these are our parent points that we're choosing to use, 2, 1, -1, and -2. So we're always going to start off with our parent points. And in this case, we're going to subtract 3 from each of those to get the points -1, -4, 2, -4, and -5. We're not moving the graph up or down, so we're not changing the y values, so that we will keep the original parent points for y, 1/2, 1, -1, and -1/2. Now, again, looking at the domain, it's going to be all real numbers except x can't equal a -3. So simply take the equation x plus 3, set it equal to 0, you'll get x equals -3. So that's going to be my vertical asymptote, but that means that the domain will exclude that value. And then for your range, there's nothing added or subtracted to the reciprocal function. So in this case, you could think of it as a plus 0. So the horizontal asymptote will be y equals 0, which means the range will be all real numbers except where y cannot equal 0 because it's undefined there. So again, sketch your asymptotes first. So I'm going to go ahead and find -3 on the x-axis and draw a dashed vertical line. I'm going to find y equals 0, which is simply the x-axis, and draw a dashed line. Again, both of those representing our asymptotes. And then I'm going to plot the points -1 and 1/2, and then the other point -2 and 1. That'll be my first branch. And then my second branch will be simply -4 and 1, -1, sorry, and then -5 and -1/2. And again, connect the dots using the asymptotes as a guide, getting the branches close to but not touching or crossing the asymptotes. Okay, got a couple more just to make sure that we got it and that we feel confident when we do our own graphing. Okay, in this equation, it's negative 4 divided by x plus 1. So we need to first identify what are all the transformations that are taking place. The negative sign means that we're going to reflect in, across, over the x-axis, however you want to say it. The 4 means that it's a vertical stretch by 4 because a is greater than 1. And then last but not least, we have a plus 1 here, so that means we're going to go up 1. So the reflection, the vertical stretch, and going up all affect the y-axis, so there's no change to our x values. So we're going to simply copy the parent points 2, 1, -1, and -2. However, for the y value, we're going to have to multiply it by a -1 because we're reflecting across the x-axis. Then we're going to have to also multiply it by 4 as well because it's a vertical stretch. So we might as well just go ahead and multiply by -4. So it'll be -4 times y plus 1 because we're going to go up 1. So we're going to take our parent points, 1/2, 1, -1, and -1/2, and then we'll go ahead and multiply each of those points by -4, and then add 1 to them. So that will give us -1, -3, 5, and 3. So these are the points that we're going to go ahead and graph. Also, let's look at our domain and our range. So here we have x by itself, so that means that our vertical asymptote is going to be x equals 0, which means the domain is all real numbers, except x cannot equal 0. So that's the only exclusion. For our range, we have a plus 1, so that means the horizontal asymptote is going to be y equals 1, so the range is going to be all real numbers except where y equals 1. That's going to be excluded. So let's go ahead and plot our asymptotes first. So where x equals 0 or the y-axis, we're going to draw a dashed vertical line. Then we're going to draw another. We're going to find y equals 1 and draw a horizontal line right there where y equals 1. So now we have our asymptotes to use as guidelines, so to speak. And then let's plot our points. So we have the point 2 and -1, 1 and -3. So that'll be the 2 points that we need for one of the branches. Then let's plot the other one. It'll be -1 and 5 and -2 and 3. And then sketch the graph there. And I want you to notice this time around, it's a reflection. So we are now in quadrant 2 and 4. In fact, let me go ahead and identify that quadrant 2 and quadrant 4 with our branches. And that's simply because of the reflection as we're flipping the quadrants that we're in. Oop, sorry. There we are. That looks a little bit straighter. All right, let's move on to the next graph. We have 3 over x minus 2 minus 2. All right, so what's going on here? This is a vertical stretch by 3. We're going to go to the right 2, and then we're also going to go down 2. So we have 3 transformations here. So let's talk about that for a moment. The stretch is going to affect the y values. The going down will affect the y values. The only thing that affects the x values is to go to the right 2. So you know if we're going to push the graph over to the right, we're going to have to add 2 to all of our x values. So let's take our parent points, 2, 1, -1, and -2. And what we're going to go ahead and do is let's go ahead and add 2 to all of those. So we're going to add 2 to all of those parent points. When we do that, we'll end up with 4, 3, 1, and 0. And then by the same token, we're going to take the parent points for the y value, 1/2, 1, -1, and -1/2. We're going to multiply them by 3 because it's a vertical stretch by 3. So if it's a stretch or compression, you're always going to multiply by that value. And then we're going down 2, so we're going to have to subtract 2. So it's going to be 3 times 1/2 minus 2, 3 times 1 minus 2, 3 times -1 minus 2, and 3 times -1/2 minus 2. And that'll give us the values -1/2, 1, -5, and -7.5, or 7 over 2, which is, sorry, -7 over 2, which is simply -3.5 or -3.5, however you want to look at it. So let's plot those points. So we'll plot the point 4 and -1/2. Then we plot the point 3, 1. That will give us 2 points that we need for the first branch. You know what I didn't do is plot my asymptotes. So I'm not going to, if I was doing this, I might plot the points, but I'm not going to sketch the graph just yet. And then the other points are 1 and -5 and 0 and -3.5. So before I actually sketch those points, let's go ahead and do our asymptotes or identify those. So again, the domain, let's look at what we've got under here with the x. x minus 2. Set that equal to 0. Solve for x. We get x equals 2. So x equal 2 is our vertical isotopes. That means the domain is all real numbers, but excluding the value where x equals 2. So x cannot equal 2. And then the range, well, look, we've got a -2 back here as well. So that means that the horizontal isotope is going to be y equals -2. That means the range will include all values for y except -2. So if we go ahead and sketch those isotopes, we'll find 2 on the x-axis and sketch a dashed vertical line. Then we find y equals -2, so find -2 on the y-axis and sketch a dashed horizontal line. Now when we connect the points for our branches, it makes it much easier to draw because we know we could use, again, using your isotopes as a guide, it serves as a border to keep the branches of your reciprocal function contained. All right, 2 more to go and then we're done. So I've got 2 divided by x plus 4 minus 7. So let's identify what's going on here in terms of transformation. It's vertical stretched by 2. We're going to go to the left 4 and we're going to go down 7. So left 4 is going to affect the x values, the stretch and the movement downwards will affect the y values. So we're going to take our parent points and we're going to, since we're going to the left 4, we need to move everything to the left. So we're going to subtract 4 from each of those values. So we'll take 2, 1, -1, and -2. And we're going to subtract 4 each time and we'll end up with -2, -3, -5, and -6. Now, it's a little bit harder on the y side. On the y side, we have a vertical stretch by 2. So I'm going to take my y values, multiply every single one of them by 2. But then I'm also got to go down 7. So I'm going to have to subtract 7 as well. So it'll be 2 times 1/2 minus 7, which will give me a -6. 2 times 1 minus 7, which will give me -5. And 2 times -1 minus 7 will give me a -9. And then 2 times -1/2 minus 7 gives me a -8. So recall that 1/2, 1, the -1, and -1/2, these are all the parent points from our parent function graph. So that's where those are coming from. And then again, let's say what is establish our domain and our range. We've got x plus 4 here. If we set that equation equal to 0 and solve for x, we'll get x equals -4. So that's our vertical isotope, which means the domain can be all real numbers except it cannot be x. X cannot be equal to -4. And then the range, we've had a we have a -7 behind the function. So it's going to be, our horizontal isotope will be y equals -7, which means the range will be all real values except that y cannot equal -7. So again, let's go ahead and sketch our graph. So find -4 on the x-axis, 1, 2, 3, 4, and then we're going to draw a vertical line right there. We would find on the y-axis -7 and draw a dashed horizontal line for the horizontal isotope. And again, those will be the borders for our branches. And then we use these points to plot our branches. So it would be simply -2, -6, -3, -5. And then over here for the second branch, we will plot the point -5, -9, and -6, -8. And then again, sketch the graph of each of the branches, and we should be good to go. All right, last one. All right. We are -1 over x minus 5 plus 3. All right, so what's going on here? It's going to be a reflection in the x-axis. We're going to go right 5 and we're going to go up 3. So moving to the right 5 affects the x values, but the reflection and going up all reflect the y values. So we're going to take our x values and add 5 so we can move the graph to the right 5. So we're going to add 5. So to be 2 plus 5 is 7, 1 plus 5 is 6, -1 plus 5 is 4, and -2 plus 5 is 3. Remember, 2, 1, -1, and -2 are our parent points. Now, to get the y values, we need to multiply y times -1 because it's a reflection, and then we're going to add 3. So we're going to take -1 and multiply it by 1/2, 1, -1, and -1/2. So look what happens here. If I take -1 and multiply it by 1/2, I get -1/2 plus 3, and that gives me a 2.5 or 2.5. If I take -1 and multiply it by 1, I get -1 times 1 plus 3, which will give me 2. Here, if I have a -1 times a -1, that ends up being a +1, right? Two negatives multiplied together give me a positive, so 1 plus 3 is 4. Same down here. If I have a -1 times a -1/2 plus 3, that's going to give me 3.5 or 3.5. So I've got all the values to plot. Now what I need to do is to set up my domain and range, and then we can go ahead and graph it. So let's go ahead and do that. So I've got x minus 5 down here, so I'm going to set that equal to 0, solve for x, I get x equals 5, so that's my vertical asymptote, which means the domain is all real numbers except the x value cannot equal 5. And then for the range, come back up here, we have a +3, so it's all the y value the horizontal asymptote is y equals 3, which means the range is all real numbers except where y cannot equal 3 because it's a horizontal asymptote, right? When we sketch this graph, notice interestingly enough, so let's go ahead and sketch it. So we've got x equals 5, so you find 5 on the x-axis, and then you go ahead and draw a dashed vertical line for that vertical asymptote. For the horizontal asymptote, we find 3 on the y-axis. Draw a dashed horizontal line for the horizontal asymptote. We plot our points 7 and 2.5, 6 and 2, so that'll be the points for one branch, 4 and 4, and 3, 4 and 4, I'm sorry, and 3 and 3.5 for the points for the other branch, and then again, connect the dots staying inside of the asymptotes. Now, interestingly enough, look at what quadrant we're in. We're in quadrant 1, not in 2 and 4, but that's because we've shifted the graph to the right so far. We went +5, so we moved the graph over 5 units. When we did that, we bumped the graph out of 2 and 4 into, because we also moved it up 3 into quadrant 1. So, but it's still, if you notice the branches, they are in the opposite, on the opposite quadrants than they were originally. Where normally they're here and here, so they're actually across from each other here. They're in the other quadrants. Anyway, that is it for the notes. Good luck with everything, and let me know if you need help.